Alrighty, let's check out the acoustics in my new quote-unquote studio. Alright, in this lecture I am working with a state space example in a practical system. And I'll just point out that the actual content here comes from ctms.engin.umich.edu. I'll drop that link in the description of the video. Alright, but what I'm working with is a magnetically suspended ball. And I'll draw a little picture for you. Essentially, I've got a voltage source here, and then I've got a resistor R and an inductance L, and then this coil of wire. And from that coil of wire, I go back to that voltage source, and then I've got a little ball, and I've got essentially a couple of things that I care about. I care about the height, and I know that this ball also has a force on it, which is its mass times gravity. And so what I'm trying to do is I'm trying to use the coil itself to suspend this ball with a magnetic field. So here's the differential equation which governs this system. So I've got md squared h over dt squared equals mg minus k, which is from the geometry of the coil, I squared over h. I'll just make a little note for you here that this k is a constant from the coil itself. Alright, then I've got v equals L di dt plus IR. Of course, this resistance and inductor are just representing the real aspects of the ideal coil. So let's actually put some values in here. So here's some values. I've got a mass, in this case, of 0.05 kilograms. I've got K equal to 0.0001. I've got L equal to 0.01 Henry. That's a pretty big inductor. I've got R equal to 1 ohm. That's pretty reasonable as well. And I know that gravity is 9.81 meters per second squared. All right, so those are my values. And what I want to do is I'm going to assume this system is at equilibrium. And we can linearize the system around a height, let's say at a height of 0.01 meters. So linearize around the point 0.01 meters for height to get our state space model. Linearization itself is not a topic of this course or of this set of lectures, but maybe at another time I'll do another lecture, and if that ever happens, I'll drop a card back in this lecture if I remember. Alright, so we're going to let our states be this. X is delta H, that's my change in height, then delta H dot, that's the time rate of change of the change of height. So if delta H is the change in height, this is the change in the change in height. And then delta I, which is the change in current. All right, and so here's what my state space model is going to look like. A is 0, 1, 0, 980, 0, negative 2.8, 0, 0, negative 100. B is going to be 0, 0, 100, and then C is going to be just 1, 0, 0. Now, if I just find the poles of A, with the poles of A, I would find that the system is unstable. And if I'm being real accurate here, I wouldn't use poles. I would correctly use the eigenvalues. But if I find the eigenvalues of A, I'll find out the system is unstable. In other words, the ball will go to infinity in height, or alternately, since it's suspended, hit the floor. However, I could check the controllability of this system. In fact, we would find out that the system is controllable. All right, so what we're going to do is we're actually going to go ahead and implement this in Simulink. So, and we're going to do that, I guess, in Matlab as well. So I'll show you that here in a minute, but let me show you what I'm going to be implementing. So first thing I'm going to do is I'm going to take my reference input, and I'm going to pass that into a summer, and then I've got U, which I'll call the input to my state space system, and then I'll pass that into B, and then I've got another summer here. We'll do a plus here, and then here I'll have x dot 1 over s to get me to x, and then I'm passing that through C to get to y. But I've got a couple feedback bits here. I've got a, which a times x plus b times u is my x dot, and then I'm also feeding that back with some k into my system here. This is my feedback control gains. So this is different from the k that I used in the differential equation. Now I have numbers. This is my control gain matrix. All right, and if I solve this out, I would identify that I actually have a small problem, and so what I might do is I might actually insert a gain, which I'll call in bar. I don't know why that's a vector, in bar or in bar. I might insert that right here in place of just an empty line here, and that's just to make sure that we're getting the appropriate gain in the system. I'm eliminating any scale factors that might be there. All right, so we're going to hop over to Matlab, see what this simulation looks like, and then we're going to wrap it up. So we'll see you over there in a minute. All right. Now we're over in Matlab and Simulink, and what I want to do is I want to go ahead and use Simulink to simulate the state space system, just so that way we can visualize it a little bit better. I've got A, B, and C defined as I showed over on my notes, and then I've got, I'll correct this here, but I'm going to place the poles using the matrix K, and then I'm going to break out those individual gains, and then we'll go ahead and calculate in bar, which let's start with the following. I want to execute up through this part, so evaluate the selection. And then now that I've got my system closed loop, let's look at where the poles of that is or are. Let's do that, finding the eig of that closed loop system, or the eig of A minus B times K. And hey, look, they actually match up with -100, -20 plus or minus J20. These poles will stabilize the system, so I expect that the system will look like well, it'll be stabilized and it'll go to an interesting spot. I'm going to actually replace nbar for now with 1, just so we can see what the response looks like, and then I'm going to simulate the Simulink file. So let's go ahead and open up that Simulink file. It's over here. I'm going to pull up the scope so we can see it. And so what I'm doing is I'm actually taking x multiplied by each of these k's, and essentially I'm demultiplexing my x signal, and then I'm doing so if you aren't sure, right here I've got the state space system represented. A, B, C, and D are constants. A happens to be a constant, which is the matrix. B happens to be a constant, which is the B matrix, and so on. Nbar also a constant, and I'm applying a step input. I want to see if this can track here. So like I said, I'll take X, which is my state, and then I'm going to use K1, K2, K3 multiplied by that state to try to drive this error to 0. And so let's go ahead and run this, and then I'll go back over to my Simulink file, pull up that scope again. All right, so the first thing I see is that this is maybe not so good. It is tracking something, but it's not tracking the unit step, literally unit step that I wanted. So it's tracking something. There seems to be some scale or gain going on that I need to figure out. So what am I going to do? Well, I'm going to come back to the rescale thing. I'll eliminate my 1, and rscale is a function I got from that website I mentioned earlier. And it's just making sure it gets the scale information out to rescale that. So I'll drop links to this or all of the code that I use in this lecture in the description below. And I'm going to put nbar to be the rscale of the original open loop system with K as my control matrix. So I've got the state space of A, B, C, and 0 with my gain matrix K. And then what I'll have is I'll simulate this. So let's go ahead and do that, and then head over to here, check out the scope, and look, I am now tracking my step input. You can check and see how this corresponds to a second order system with zeta and omega n values as far as time to settle and percent overshoot. You'll see that the place that I put my poles was -20 plus 20i and -20 minus 20i, and then the other one was really far into the left half plane, so the complex conjugate pair, which is closer to the j omega axis, is the one that's going to matter far more, as long as that second or that extra third pole is way far away, and so the response should look fairly close to this. You can do a lot more exploration with this, but I just wanted to give you an example of actually using a system with a reference input. So in the previous lectures I showed you what happens when I do control, and I'm just controlling the initial conditions to a response. Here I wanted to show you what happens with an actual reference input. Alright, so that's all. Thanks for watching.